Come on in, everyone. Anybody have any questions? Feel free to ask them. We got about 5 minutes before everything starts up again. Good job. Been there.
All right, so here's my question.
Good for it.
So I'm looking at the Canvas, and I'm seeing a total of 3 tests that we have. One for chapter 1 and 2, one for chapter 3 and 4, and today's face-to-face, which is chapter 1, 2, and 3.
Right.
And that's correct, that there are 3 tests due pretty much by the 26th.
Yes.
Okay, I just wanted to verify before I
Yeah,
work
you
some
have
things out.
lab tonight, so y'all be doing that one when you get there. And I have one student that's actually doing it via lockdown browser, but and webcam. But yeah, that works. Anything else?
Well, on the lockdown browser one, is that an option, or is it you prefer
If you
face-to-face?
can't make it, I have a student that's driving a couple hours to get here, sort of like me. So, well, I only have to drive about an hour to get there, but that student asked if they could avoid the 2 hour drive on test days, and I said yes. So I'll just record it with the video. If that's something you wanted to do, that's something you can do at home or whatever. That I don't mind. But I
Okay,
only set it up for that student, so you can do it next time. Just because I only have one set up, but you can
okay.
certainly next time if you want.
I've done that before in my calculus class, so I mean not unknown to it. So, but
Yeah, I try to when they do that, I try to get them to have a mirror behind them so I can keep an eye on everything. But that's the only extra requirement I usually give.
okay, sounds good.
All right. Anyone else have anything? Still got about 4 minutes.
Last question on the test. Are
Go
we
for it.
allowed to have like a formula sheet?
Yes, yes,
Okay,
and it's any number of formulas. You don't have to, it's not like limited to a single page or front of a page or anything like that. The only thing is, as far as your course goes, you're only allowed to have the equations that are numbered in your textbook.
gotcha.
Are you familiar with what I'm talking about as far as the numbered ones go?
Yeah, I mean, all my notes are handwritten, so I didn't write down the actual numbered ones.
Yeah, you don't need the
I didn't.
numbers. It's just those are the ones I allow you to use. So like when you take them, your instructor might actually your lab instructor might look at them and confirm that they're that, or sometimes the lab instructors will actually take them up. That's what she did last time was she just took them all up and then we go and look at them and make
Okay,
sure they're all okay.
all right, sounds good. Thanks.
All right. Good luck. It was not supposed to be, but a student contacted me Friday and said that it was doing that. So I think, as far as I know, I fixed it, but I'll check and make sure it's fixed still. Practice test 3, edit, looking at it. Oops. It for some reason only allowed one attempt. So I don't know why. Oh, okay. It was a different class that someone had recommended or had let me know that it was uh only one attempt. But you do have time to do it again now if need be. Wish somebody would let me know that. That would have helped you guys. Well, I mean, you had it with your practice test too and all that stuff, but yeah, it sucks. Anyone else? So I got it up now. It does say unlimited attempts. So at least we have that. That should be pretty quick. All right, got about one more minute. Oh yeah, that's right. You guys are 241. It was 242 that contacted me and said they had only one. It was so weird. I don't know why I copied over and it's supposed to have the same number of attempts, but evidently I didn't do it. So you want to know how to go about looking so handsome? This is what you got to do. That's my story. I'm sticking to it. Is a practice test a percentage of your grade? So no, but doing the practice test one is really, really smart. But the other thing is too, it also gives you an extra credit. So for instance, at the end of the semester, I take your highest score on each of the practice tests. And if you missed one, you get a 0 for that one. But I then average them and I divide the average by 20 points, and that many points is added to your course grade. Yeah, normally your practice tests are supposed to be an unlimited number. I have no idea, one, why that one only had one attempt, and two, why nobody else let me know. But I wish someone would have. So please, in the future, let me know that, because that just, that destroys your chance. Even though you have a lot of chance to practice with your test one and test two, and those were all already open. But yeah, there's one extra chapter in there that would have been helpful to you. Actually, let me see. Actually, no. So you had plenty from just your practice test one and two. So there wasn't even an extra chapter in there. But yeah, at least you would have had more attempts for just that one. Let me check. Logan. Ooh, that's weird. Okay, got more people admitting. All right, so it's about time to class. Logan, I can't find it right now, but it just locked me out of my email. So anyway, sorry about that. And you hopefully you saw that your test is available there, Logan. All right, we need to go ahead and get started, everyone. I want to try to finish up a little early so y'all can have some more time to go take the practice test before the test occurs. That would be wise. Uh, Again, the more chances you get, the better. But like I said, if you've been taking practice test one or practice test two, you've been getting plenty of practice. Trust me, way more than the regular than the test itself would do, just because you're doing multiple tests and in a more detailed way. But when we last spoke, we were starting to show you how to use Newton's second law. And Newton's second law is the summation of the forces, meaning all the external forces acting on a body of mass m, which I indicate by a sigma followed by an F. The summation of the forces is equal to mass times acceleration. And right now we're dealing with forces that are constant, so the accelerations should be constant as well. And that's a simple version of Newton's second law. Eventually, Newton's second law will become the summation of forces is equal to mass times dv dt, where dv dt is the derivative of the velocity and therefore the acceleration. But in principle, the f's on the other side could be functions of velocity or time for that matter, and stuff like that. And then later we'll even say the summation of forces is equal to dp. That's d is in derivative of p, the momentum. P is in person. P, the momentum with respect to time. And again, that's another instance where it could be something where you don't have a constant force, and therefore you don't necessarily have a constant acceleration. I can't check my email right now. I'm not sure if I did or not. Did you see the email about me not being able to? Okay, so Anissa, if you're having that problem, can you stay at the end of class and I'll hook you up with a way to get that done? If you can do that, we'll work it out. It's not a big deal. You have a class tonight that interferes with your lab?
Yes, I do. My class starts at 7,
How do you
and
know
it's
it's lab?
because this one it's async. Yeah, I'm
Okay.
messing up the word, but
Okay.
I so it's on certain days, and with the lab instructor, I did tell her all the days I
Oh,
won't be
okay.
able
So you got it
to come
cleared ahead of
there.
time. Cool.
Yeah.
That's not a problem. Yeah, I can just I'll make up a separate version for you and make it available. What you can do is you can take it at home and use the camera. Do you have a camera on your computer?
Yes, I do.
Okay, so you'll do it just like my other student is. So I'll make another test and I'll probably put your name in the title, or it'll just say respond this with I think the wording it says respond this lockdown browser and what else does it say? Monitor. I think it has the word monitor in it. Yeah, I'm looking at it now. Yeah, and webcam says plus webcam. So I'll make another version for you. That way, for starters, don't talk to anyone obviously about what's on the test, and obviously no one should talk to you about what's on the test because you'll get an unfair advantage. But so there might be a little bit of overlap, at least in the content, if not the exact question. So I'll make you another one so it won't be that much of a problem. Okay. All
Okay,
right.
thank you.
You're welcome, Anissa. So we were talking, as I said, about Newton's second law. I've got a couple other equations or a couple other concepts I want to square with you. So basically, we've done all of chapter 4 right now. And in fact, all we need to do is go on to chapter 5. So last time I even showed you an inclined plane. I showed you the fuzzy dice problem. I showed you the Atwood machine. So those are really the major things because the Atwood machine requires you to solve a system of two equations, two unknowns. And that was something that I needed you to see. I also needed you to recognize that it was a same technique that you learned in high school algebra, and then, of course, it later in pre-calculus as well. And then the fuzzy dice was one where we were using a technique that physicists use, but you don't normally get in your math classes. So I wanted to make sure you guys had seen that. And then the inclined plane problem has you using a tilted coordinate system, which is a whole different weird kind of ball game. And by using that tilted coordinate system, that made you have to convert a vector or reduce a vector down to its components parallel to that tilted coordinate system. So that was the main points in the problems that I was doing and why I was doing them. So in chapter 5, the difference is we are now going on to introduce friction, and we're going to introduce a centripetal, Centripetal force. So the centripetal force is a center-seeking force, and it's really the force that's necessary to keep an object going in a circle. Or if it's not a circle, it could be an ellipse, but still you need a center-seeking force to make something go in any kind of orbit for that matter. So we're going to do that. I'm going to motivate a way for you to think about it, and I'm going to go ahead and solve another inclined plane problem. So first off, I think I wanted to solve an inclined plane problem that's kind of interesting. So what I'm going to do is I'm going to draw an inclined plane. I'm going to use just plain symbols here. So we don't actually deal with numbers. We're just dealing with symbols, and therefore we get an answer that's always right. Okay. So what I am going to do is I am going to draw an inclined plane, let's say like this. And of course, I'm not going to use the thing that makes the line nice and straight because that would make it pretty. Okay, so I went ahead and redid it. And you're going to have to, of course, want to see the thing that I'm drawing, which I've neglected to remember to do. So now I'm going to share my screen because that evidently comes in handy from time to time. It's like I've never taught before. It's just every day is a new day. Okay. So I did do the same thing I did in class today. Specifically, I seem to have made this inclined plane really, really, really steep. So what I'm going to do with this inclined plane is I'm going to show that it's tilted at an angle of theta. Okay. And then I'm going to put another inclined plane on top of it. And this inclined plane is a similar inclined plane in the geometric form of the word similar. Okay. So it has an angle theta, and you can sort of imagine it having some wheels, and then on that is a little scale. And then standing on that scale is a person of mass M. And what I want to do is solve for the apparent weight. So what is the apparent weight of the person? So that's really what we're trying to do here. Okay, we are going to assume that we know the mass M. So M and theta and G, gravitational acceleration, are known. So of course, what that means is if we're on planet Earth, we're just going to use 9.8, but because I'm doing it in terms of G, I could always replace it with the gravitational acceleration of some other planet. Okay. So what I've got to figure out is really what is the acceleration, because what's going to happen here is because this person is standing on an inclined plane that's on an upside down inclined plane that's on a, and then on a scale on top of that, the scale is not required to hold up the person's entire weight, because the person is making some progress in falling towards the center of the earth. Of course, they're moving left and right too, so it wouldn't necessarily be an easy thing to accomplish from a balance standpoint, but that's not really our concern here. We're just trying to figure out what would the weight be. So here's my solution.
I have a quick question.
Yes.
I just thought about this. So on the test, if we're given like a value such as G, do you want us using 9.8? Do you want us to use 9.81, 10?
Yeah, we use 9.80, but yes.
Okay, sounds good.
No problem. So what I'm going to do is I'm going to draw a tilted coordinate system. And I'm going to draw it like this. So I'm trying to make it look somewhat like the tilted coordinates are like the inclined plane. Okay. Oops. So this axis is going to be my y prime axis. This axis is going to be my x prime axis. And then I'll also reiterate that this angle is theta. Okay. Now on it, we have a person of mass M. Okay. So I'm really just drawing the free body diagram for the person. Now, acting in the vertical, or excuse me, in the positive y direction, I'll use a green vector. We have, in fact, in this case, I really didn't do that as well as I'd like to. In this case, we have a vector acting upward that you can sort of think of as maybe the normal force. Really doesn't matter too much. It's not really our concern. What we are more concerned with, in fact, is this weight that is just M times G acting downward. Okay. Now that actually results in a negative Y component of force. And by the way, since this angle down here that I've drawn is theta, that means this angle is 90 minus theta. And therefore, this angle right here has to be theta again. So you can see that this one is mg cosine theta. Similarly, there is a x prime component of the weight that points down the incline, and that one is mg sine theta. Okay. Now, all of this is somewhat relevant. The main thing that we're trying to figure out is what is the acceleration down the incline. So I need to figure out what is basically the acceleration going down the incline. So I'm going to take my summation of the forces in the x prime direction is equal to mass times acceleration in the x prime direction. And you can see from this, there's really no left-right forces. There's no positive x prime force other than the mg sine theta. And there's no negative x prime force. So really it's just mg sine theta is equal to max prime. And of course, from that, you can see that ax prime is equal to g sine theta. And we're going to call that equation 1. Now, that's not necessarily that helpful. It just tells us how fast the little tilted, flipped upside down inclined plane is going to go down the inclined plane, and therefore how fast the person is going to drift downward. But really what we need to make sense of how much weight that person appears to weigh, in other words, what's the scale, what force is the scale having to provide? In order to see that, we really need to know what the vertical acceleration is. So now I've got to draw yet another coordinate system. And in this case, I'm going to draw a coordinate system that's horizontal. So here's my x-axis. And here's my terrible y-axis that I'm very disappointed in. So I'm going to draw again. Okay, close enough. So there's my y-axis. And there's my x-axis. Now this time, again, we have a mass m, but what we have is a F scale pointing up. And that's the force that the scale has to apply. So I'm also going to call it weight apparent. So I'll just say weight AP, WAP for weight apparent. Okay. Now, in addition to that, I have a force acting downward. And that force, of course, is mg. And from the summation of the forces in the y direction equals mass times acceleration in the y direction. From that, I get WAP, which is what we're wanting to know, minus mg is equal to MA sub y. Okay. Now, that a sub y is a bit problematic, but for starters, we should mention that a sub y is actually going to be a negative quantity. So I am going to put that in. But first off, let me look back at what our acceleration that we found was. And what we found was this a sub x prime is equal to g sine theta. So that can be broken up, in fact, to again, this angle right here is theta. And this is going to be ax prime times, basically, if we wrote sine theta, we'd get opposite, which is ax prime over adjacent. Oh, excuse me. Sorry about that. I shouldn't have called that ax prime. I wasn't really calling it ax prime. I was planning on writing it in terms of ax prime. So let's call this the hypotenuse. So I'll just say h. So I'll put this back in here. I'll put this in blue, and I'll say this is h, say. And by doing that, I can see that ax prime, the acceleration down the incline. No, that's not what I want to do either. Dang it. Sorry about that. I've gotten myself bogged down in a bunch of symbols like a goober. So what I do know is that hypotenuse of that triangle is, in fact, ax prime. And that's, I'm not going to call that h. I don't think I need to. I think I figured out a way where I don't need to do that. So let me make this a little bigger and clear that out. Like that, like that. Okay. So this one's going to be a sub y over here. So, and this one right here, which really should be in a positive direction. So let me draw that with the appropriate color. That's a sub x, but we don't really need it. I just wanted to show you what it was. So now what I'm going to do is I'm going to say that sine of theta is actually equal to opposite over hypotenuse. So that's AY over hypotenuse, which is G sine theta, or another way we could say it is it's just AX prime. So that was the main thing I was trying to get at there. So from that, we can now say that AY, and again, this is where I'll put in a negative sign, but right now what I can say is AY is G sine squared theta. So I'm going to take this equation, which I wrote in green. I'm going to call that equation 2, and I'm going to take this equation, which I wrote in blue. I'm going to call that equation 3. So now what I'll do is I'm going to combine uh, 2 and 3. So what I have now is weight apparent minus mg is equal to m times, here's where I'm going to add my negative, g sine squared theta. And you can sort of think of that as me just making sure that I get a negative quantity, because the actual acceleration will definitely be in the negative y direction. So that makes some sense. Now, if you go to solve for this, we can now say WAP is equal to mg minus mg sine squared theta, which equals weight apparent is mg times 1 minus sine squared theta, or finally, using a famous identity that you probably all know, hopefully, you just get WAP is equal to mg cosine squared theta. So that's the actual apparent weight. And you should consider, you know, special angles or extreme conditions. So for instance, if an object, if the incline was in fact flat instead of no incline whatsoever, or as meaning no incline whatsoever, what would you expect the apparent weight to be?
mg.
Yeah, you just expect mg, right? So if incline were level, that would be theta equals 0. And what you get is WAP is equal to mg times the cosine squared of 0. And of course, cosine squared of 0 is just 1. So you get mg. And that's a nice little check. Anybody have an idea what your apparent weight is if you're in free fall?
We don't have one.
Yeah, it's actually 0, right? You're weightless. So you'd expect that to come out too. So if theta equals 90 degrees, then W apparent is equal to mg times the cosine squared of 90 degrees. And of course, cosine of 90 is 0, so you get 0. So there's another check. So that's something you always want to try to do when you're solving problems. You want to try to use your physical intuition to check the extremes. For instance, we're going to do Atwood machines like we did last time, but we'll do Atwood machines on inclined planes. And if you let one of the angles of the inclined plane go to 90 degrees, then that inclined plane should be acting just like the Atwood machine with a vertical rope. So you should be able to get the same formulas you had before. So that's something you always want to do when you're solving physics problems. It's sort of like me being a theorist. This is sort of a theoretical thing that you do, but it's not unlike in experimental science when let's say early in the 1900s, it was slowly coming to realization that, or people were coming to the realization that the earth might be very, very old. They were seeing ideas, even, from, for instance, the theory of evolution, that species would actually change over time and become new species and stuff like that. And if that was truly the case, then, some of the older ones would be ancestors of some of the newer species. And they estimated that it would take a long period of time to do that, multiple hundreds or thousands or hundreds of thousands of generations, which would suggest the earth had to be, hundreds of thousands of years old and stuff. That wasn't consistent with what we thought beforehand. But when we also learned later about the Big Bang, and later when we learned about plate tectonics, we discovered how slow the continents and the continental plates were moving. And when you sort of work that math back and forth, you'd say, oh, well, the idea of continental drift is suggesting that these two species would have been separated from each other, let's say 60 million years ago. And then you find out that that's completely consistent with the biologists estimating the number of generations that have to pass for these two species to diverge from each other. And then you'd say, well, wait a second, what about, astrophysics? Is the sun possible to have burned that for that long? And then lo and behold, out came E equals MC squared. And we realized there was another mechanism by which the sun could burn, and that was nuclear fusion, as opposed to coal, which we had basically estimated. Lord Kelvin had done a calculation assuming the sun was as massive as we knew it to be, and that it was in fact made of the best burning thing that we had found, which was coal. So if you actually imagine the sun being coal, you can sort of estimate about how long it would last. And I think the calculation was it would be on the order of 50,000 years. If you go back through Genesis and the begats, you would find that that's probably on the order of 10,000 years. So everything worked with our historical record, which literally was the book of Genesis. So everything was cool. But then when you start bringing in all these different species and all plate tectonics and the idea of the Big Bang and all that stuff, then all you had was a bunch of different sciences all pointing to the same time frame, and that gave you more confidence that the time frame was reasonable. So that's the same thing we're doing here, only here it's not experimental, it's just with an idea. So you still want to do that as much as you can, whether it be an idea or an experiment. Or what I've always tried to tell my students is when you're learning to solve physics problems, you're basically employing the scientific method to see exactly how you solve a problem. You might not know how to do a particular type of mathematics problem, so you try a way that you think might be right. You check, see if you get the right answer. If you don't, you say, well, maybe I didn't do it right. You check for errors. You still don't find anything. So yeah, you say, okay, I didn't do it right. You try another way, then you get the right answer, or what the book calls the right answer, and then you're more confident. And slowly, piecewise, you can learn math that way as well. So anybody have any questions on that before we move on to the next problem? All right, so that's another neat little problem. What I want to do now is I'm going to take a very specific, what we call a vector function, a multi-valued function. So this is really some highbrow mathematics. We're going to introduce you, or I'm going to introduce you to a vector function. And what I mean by that is a vector that's a function of time. And because it's a vector, that means it could have an x component, a y component, and a z component, but it's also a function of time. So unlike a regular function, you're used to like f of x equals sine x. Well, you put in an x, you get out a number. In this case, you put in a number, you get out two components. So that's a little different. But I'm going to make a very specific one. The specific one I'm going to do is I'm going to say r times the cosine of 2 pi over t times lowercase t, where lowercase t is the time. I'm going to multiply that by I hat, and then I'm going to take r times the sine, again, the same argument, 2 pi over capital T times lowercase t, j, and we'll figure out from the actual graphing that I'm getting ready to get you to do, we'll find out exactly what that 2 pi and what that capital T means. So what I'm going to do first is I'm going to make a table, and the table is going to consist of times. And it's obvious. Whoa, I don't know what I did there. Okay. I wanted to undo that last thing I did, but there we go. I hate it when I draw crooked lines. So I'm going to draw a straight line this time. So there's my time. I'm going to say R of, well, okay, there's the problem with drawing straight lines is it doesn't recognize regular symbols. So I got to take it off of straight lines. And actually, I should write this is R of T. And now I'm going to write X. Again with a straight line. And then I'm going to write Y again with a straight line. Like this. And my first time, I'm going to say 0. So if I plug in t equals 0, you see that the cosine of 0 is in fact equal to 1. So this is just r I hat. And then, of course, the sine of 0 is 0. So I get no j hat there. That means the x is going to be r and the y is going to be 0. Now, my next amount of time I'm going to try is t over 2. If you put in t over 2 there, you'll see that t over 2, actually, no, I want t over 4, not t over 2. So let's write t over 4. So if I put t over 4 in for lowercase t, you see I get 2 pi over capital T times capital T over 4. So ultimately, I'm just going to get pi over 2 for the argument. So cosine of pi over 2, of course, is the cosine of 90, and that gives me 0 for the I hat. But the cosine of the sine of 90, of course, gives me 1. So that means I'm going to get R for the Y component. So in this case, I'm going to say R J hat. That means X is 0 and Y is R. Now I'm going to say 2 pi over T. Actually, I'll just call it 2 pi over 4 or 2t over 4, which is, of course, t over 2. So with t over 2, now the t over 2 times 2 pi over t gives you basically just plain pi. And pi is 180. Of course, the cosine of 180 is -1. So that'd be negative r j hat. Of course, that's negative r for x. And now if you do pi for sine, you get 0. So that's going to be 0 over here.
Wouldn't that be negative r I hat?
Oh, thank you. Yeah, nice catch. Yes, I should have wrote that. But anyways, yeah, I wrote the wrong one. So thank you. I hat, thank you. And this is negative r, and this is 0. And now I'm going to do 3t over 4. So as you can tell, I'm going to have to extend these lines a little bit. So at 3t over 4, basically you're going to get 3 over 4 times 2 pi. That would be 3 pi over 2, which is 1.5 pi. So 1.5 pi for cosine is 0. So I get 0 I hat. But 1.5 pi for sine is -1. So this is going to give me negative r. And this time it really is j hat. Like that. So that means this is 0 and this is negative r. And then finally, I'm going to say just plain t. And when I get just plain t, I've got the cosine of 2 pi, which is 1. So that gives me r I hat, and then r, and then 0. So if I go to make such a coordinate system, like so, okay, then I can say this is going to be my x-axis, this is going to be my y-axis, and in fact, if I let r be, let's say 3 squares, like this, then I can attempt to draw a circle. And look at that. I drew a perfect circle. Okay, I might have cheated a little bit, but y'all get the point. Okay, so there's a, and actually it didn't come out to be a perfect circle. I'm a little aggravated that it didn't. Should have come up perfect, but I did everything else right. Okay, let's see if I can do that now. There you go. That's much better. Okay, so now we've got basically a circle. So what we've managed to draw here is I'm going to use black to represent the R vector. So this guy right here is R of 0. Okay. And then you look over here, and this is R of t over 4. And this is R of t over 2. And then this one right here is R of 3t over 4. So you can see basically in succession, it is pointing around the circle to each of these spots. And you can see basically this looks, and if you did more angles, if you tried pi over 8, or excuse me, t over 8 and 3t over 8 and all that, you would see that in fact, as this thing goes, the R vector is circling around the origin, pointing to these locations, and such that it's basically the dot is traveling around in a counterclockwise circle of radius r. Does that make sense to everyone? So that distance is r, that distance is r, that distance is negative r, and that distance is negative r. Okay. So I'm now going to see if you guys can do this. Let's say v of t, which we know is dr over dt. Let's compute that. I will show you the first term. Remember, the nature of taking derivatives and integrals of vectors is that if you use I hat, j hat, and k hat, they just act like constants. So I'm going to do the first term of r hat, or excuse me, of r vector to compute what the I hat component of the velocity is. So the derivative of r cosine 2 pi over tt with respect to time is going to be the derivative of cosine of u. Of course, the derivative of cosine is negative sine, but then I got to take the derivative of u with respect to t. So I'm going to say negative 2 pi r over t sine 2 pi over big T times t I hat. So that's the first term. Now let's let you guys go ahead and see if y'all can compute what the second term is. So I think I've given you a little bit of time here. Remember, the r is a constant, the j hat's a constant. We're taking the derivative of sine u, and then using the chain rule, we got to take du dt. So the derivative of sine is cosine, and then the derivative of 2 pi over t times t with respect to lowercase t is 2 pi over t. So I'm going to say now this is 2 pi r over t times cosine of 2 pi over capital T times t. And like I said, the r and the j hat are just constants, so they just end up like that. Now, if you were to take the time to actually plot v, I will tell you that v at t equals 0, when t is equal to 0, the x component term is 0, but the y component term is positive. So you're going to get something that looks like this. So that's v of 0. And sure enough, if you plot this, this would be v of t over 4. This would be v of t over 2. And this would be v, and this is supposed to be perfectly horizontal, by the way, even though I didn't draw it that well, 3t over 2. So you can figure out that, and that's one of the things I'll let you do for extra credit. But here's something neat. Let's see, can you guys actually compute what v of t is? Can someone compute the magnitude of v of t? I think you'll be surprised. What? Go ahead.
Oh, is it the radius?
Very close. You're missing a few little giblets, some factors, but yeah, you're close to it.
I was just taking a guess.
Okay. So remember, the x component is parallel to the x-axis. The y component is parallel to the y-axis. So they're perpendicular. So you think there's some kind of famous theorem we might be able to use to figure out the magnitude? Now you can also realize that this is going to be like that. And I think you'll see that it's ultimately just going to become 2 pi r over t. So see how the sine squared plus cosine squared equals 1 came into play? All right, can anybody tell me what that value is geometrically? We just computed the magnitude of the velocity. Can you use your knowledge of geometry to give me some idea of what that velocity is, that magnitude is? Do y'all see that that is circumference? And do you see that this is something we call the period? Notice at t, we got exactly back to where we started from. So what we say is the period is the minimal time required for motion to repeat itself. And we can see that within a time period of t, we did in fact repeat ourselves. We went from r I hat to r I hat in time t. So if we divide the circumference by the period, we're really getting the what appears to be the constant velocity of the object going around in a circle. Okay, so that's what the velocity is. That's kind of interesting. Now let's try one more because this is really relevant. I'm going to say a of t is equal to dv over dt. Let's let you guys go ahead and compute the x and y components of this, and then I'll do it, and we'll make sure we get the same answer. So hopefully everybody was able to get that. I would like to point out that you could, in fact, write this as negative 4 pi squared over t squared times, in fact, r vector. Okay, so you can see it actually points radially inward because the r vector pointed radially outward. So you should see that this would be A of 0. And this would be A of t over 4, for instance, and so on and so forth. Now, the big thing is, I would like to calculate the magnitude as well. And the magnitude of this, anybody want to give that a try? So hopefully you're able to come up with that. Now I'm going to do some trickery here. I'm going to multiply by r over r. And the reason why is I wanted you to see, in fact, that there exists a quantity, omega, such that v, the magnitude of the velocity, is equal to r times omega. And omega, if you're looking at it this way, that means omega is equal to 2 pi over t, which obviously has units of radians per second. So all of you are way too young to know this, but us old people used to listen to these big plastic black discs. And these big plastic black discs rotated on a little spindle, and it had a little arm that would lay on it and a little needle that would vibrate from the little paths and grooves on the disc. And you would set the speed of the disc rotating to whatever the appropriate speed was for the black disc. So the black disc would say, you know, this speed or this speed, and 33 1/3 was one of the speeds, but it literally meant 33 1/3 revolutions per minute. So you can see this omega is the same sort of thing. It's called an angular speed. It's also
Some of us remember.
yeah, some of you remember. It's also called an angular frequency. So that's angular speed r frequency, which we just use f, because it turns out if that t being the period also means t is equal to 1 over f. So you could also say omega is equal to 2 pi times f. So all of that combines to let us see something, specifically v equals r omega, which comes in super handy in chapter, I think it's 10, when we start studying rotational motion. But if you do this r times r, or this r over r thing that I was doing on the red work, what you end up getting is 4 pi squared r squared over t squared times r. Well, this looks a lot like 2 pi over t squared times r squared over r. And of course, 2 pi over t we know is omega. So that's omega squared r squared over r, like that. So we could actually do that as well. And we're getting somewhat closer. But if we instead decide to go 2 pi r squared, that's actually, let's do 2 pi r squared over t squared, like this. Okay, then what we can see is all we've got left is 1 over r, but that 2 pi r over t, we already figured out what that was. That was just v, so we get v squared over r, and that's the actual centripetal acceleration we were working on. So a centripetal is equal to v squared over r. Of course, is also omega squared, well, we could say omega squared r. that's another acceptable version, because you saw that we did get omega, or we got 4 pi squared over t squared. So that's omega squared r. But honestly, I almost always use it in the form that I wrote here with v squared over r. So that's a really big deal. That is actually the acceleration necessary to keep an object going at a constant speed of 2 pi r over t, and going in a circle. Okay, so if we want to calculate how much force is required to allow a car to make a turn, then we need to understand that it's the friction between the tires and the road that allow the car to make the turn. And we need to understand that the force has to be sufficient to make the centripetal force. In fact, this I mentioned this in class today. Back in the, I want to say, mid to late 90s, might have been even the early 90s. There was a story on 60 Minutes where these people got together and they did something that's really common now. I've seen a ton of videos, people doing it on YouTube and stuff like that. But they would go like to, let's say, Grand Teton Park or one of those cool parks in Utah, and just like connect a rope to a big old rock structure and then jump and swing on the rope. You know, that's kind of fun and exciting stuff. So they were doing that, and they were really way before their time, because people do it all the time now. So the main guy had an idea. He wanted to do this on the Golden Gate Bridge. And I don't know if you realize this, but the Golden Gate Bridge is one of those bridges that's so high that people use it to commit suicide, because it's literally high enough that when you hit the water, you're going so fast you can die just from the impact with the water. So this was a neat thing, quote unquote, neat thing to do, but he didn't really understand some of the physics. So he got him and his friends together. He was wise. He went ahead and measured each of them's weight. And he went to the local hardware store and found a cable that was more than sufficient to hold their weights. I think it was even like twice as much as the weight of the people combined. So he did that, and then he made this really long, like 90-foot rope, and they pulled it taut, and they all had harnesses on like you do for rock climbing. They were all bolted together, and they began to swing down from the Golden Gate Bridge. But they got on the order of 30 to 45 degrees down, and the cable busted, and a couple people hit a boat. One person's quadriplegic for the rest of their life, but it's all because he didn't understand that you're not just holding up the weight of the people when you're trying to let them swing. You've got to hold up the weight, and you've got to provide the centripetal acceleration necessary to keep it going in a circle. And that is what exceeded the capacity of the cable that they used. It broke. He got sued, and he ended up in prison for basically being reckless, not planning ahead. But in some sense, it was somewhat reasonable that he didn't spend too terribly much time. I think he got on the order of a few years, but it just was a bad case where someone just didn't understand physics, and that's a problem. Okay, so keep that in mind. If you actually, ever want to have to do anything like that, you got to realize it's not just your weight that you got to hold up. It's got to be your weight plus the centripetal force. So let me show you something else that I wanted you to know, and that is the friction force. So the demonstration I normally do with my students is I tell them, here's my calculator, and my calculator has these nice little rubber feet, if you will, on it. So they're actually kind of grippy, if you will, and you can put it on the surface of the desk. And when I try to push it to slide it along, what I discover is it's kind of hard to get it started. But once I get it started, it feels like it gets a bit easier. You should all try this yourself. When you go to push it, it takes quite a bit to get it started. But once it's started, then it easily slides along. Well, that actual fact should be something that the equations show us. And in fact, we're going to talk about specifically 2 types of friction. So the 2 types of friction we're talking about, we have static friction, and that is labeled F static is equal to, and I'll do it like this. This might seem a little bit weird, but it's less than or equal to mu static times the normal force. So that normal force that we kept working with last time, I told you we didn't really need it. Well, here's where we need it. Okay. So that's one case. And in fact, if you were to make a graph of the static force, the static friction force versus the applied force, what you'd get is F static here, and what you get here is F applied. And what you would see is that if you apply a force of 2 newtons, then the friction force would apply a force of 2 newtons. If you went up to, say, 8 newtons, then the friction force would actually accommodate it and say 8 newtons as well. So that's really good. But what ultimately happens is you get up here and you get mu static times the normal force. And what happens there is this straight line runs in right there. And what we find there is this is also mu static times the normal force. But at that point, that's all the force that the static friction can hold. So this less than or equal to says, hey, it's never going to apply more friction force than the applied force. And it can only apply a friction force up to a maximum of mu static times Fn. And this mu static is called the static coefficient of friction. Your book has a table of these quantities. And of course, we'd have to give it to you in a given problem. So that's good to know. But just as a touch point, if you want, for instance, wood on wood, the friction force mu static is equal to about 0.4. Okay. Now there's another one called kinetic friction. And that's the friction where the surface is moving with respect to the surface that it's on. And in this case, what we get is kinetic friction is actually exactly equal to mu kinetic times the normal force. And for wood on wood, it turns out that mu kinetic is equal to 0.2. Now, that's not a happenstance. That's actually the reality, is that the static friction force is always greater than the kinetic friction force. That's exactly why when you push the calculator, it has to get up to some max value of your force before it'll start moving, but then it moves easily because then you're actually pushing it in the kinetic friction mode. And it's also the reason that we turn into the curve when we're, for instance, driving in the snow and stuff like that. So those are the 2 formulas that you can use. Your book will show you examples of how to apply that less than or equal to scenario. In fact, when you get to your dynamics class, most science, or at least most engineering students, will have a statics and then a dynamics course. And in the dynamics course, they give you some really good ways to think about in a structured way exactly how you're going to solve such problems. That's a little nicer to deal with, but we don't do it that way in physics. We sort of want to not take the creativity out of you. We want you to come up with your own ways to do it. So we don't give you little algorithms and step-by-step processes. We just want you to try to figure it out. So just be advised, you now have all the tools you need. You need A equals V squared over R, for instance, to calculate the centripetal acceleration necessary to maintain a circular path. And that's, of course, a path moving with a constant velocity V that's equal to 2 pi R over the period. And you need, of course, to understand kinetic friction and static friction. Next time, we're going to do nothing but solve problems related to those, but I'm going to go ahead and let you guys go a little bit early, only a couple minutes, but I want you guys to go have a little bit of time to at least take a practice test. But have a good one. Good luck on your test. I hope you do really well. Ask your teacher if you have any questions about any particular problems. For instance, if you need a constant like G or something like that, she can probably help you. and that's okay. But of course, you're supposed to have your equation sheet, so make sure you got that. Have a good one, and I'll wait for the last person to leave in case anybody has any questions.
Okay, I got like a series of questions here.
Mhm.
I got some questions.
Go for it.
So on that graph, shouldn't like you mentioned that kinetic friction will always be lower than static friction?
Mm-hmm.
Shouldn't there be a drop off on the graph where like where you see a break off from static friction and kinetic
Yeah.
friction?
Yeah, I was just sort of giving them a rough estimate, but yeah, absolutely. If you want to really be specific about it, the correct version would be something like this, and then maybe like that, where
Okay.
this quantity then would be mu kinetic times Fn. So yeah, absolutely right. That's the way it should be. I was just trying to give them a rough estimate, but yeah, I should have done it more precisely and said exactly what you said. So thank you.
Okay, yeah, I just got confused about that. Also, I've probably asked you about this before.
Mm-hmm.
This test, it's in person at TCC, right?
Yes,
So-
in your lab.
So I have a graphing calculator. Can I use that?
Absolutely.
In
Yep.
84?
I allow
Yep.
graphing calculators, programmable calculators, all that good stuff.
And the formula sheet includes all the ones from the book, plus like basically anything you bought.
Yes, I said there was a couple equations that I derived for you guys regarding projectile motion, like the range, the hang time, that sort of stuff. You're allowed to use those even though they're not numbered, but all the other ones are only equations that are numbered in your textbook.
Okay, that's about it. And about the practice test, I didn't take it because I saw there was only one and there was only one available time you could take it.
Right.
Is that since I didn't take it, does that count as like a negative grade in my direction?
No, if you you didn't do it at all,
No,
I would definitely do it at
figured
least
something was wrong.
once just to keep from getting a zero.
Okay.
Because it is free points at the end of the semester.
Okay. I went to go do it in the beginning of class, but I noticed that was locked.
It normally disappears right at time for for the test to start. What I'm going to do right now is I'm going to make sure that's not the case. I'm going to give you a little bit more time just because I screwed up. It's the least I can do since it was for some reason only showing that. Yeah, it only shows up till 5:20. I tell you what I'm going to do. I'm going to put it till the 26th. There you go. So y'all have until 5:20 tomorrow to do any versions. It's kind of a bummer because it's not going to help you as much, but still at least you can get some in and get, 100 score to help your grade if you want.
Okay, that was it. Thank you.
No problem. You're welcome. Anybody else? I stopped sharing the screen just in case anybody had any other.
Yeah, I was just making sure that you got me on this from your 12 o'clock class.
Oh, gotcha. This is.
Yeah, I sent you the email today.
Okay,
just wanted
gotcha.
to make sure I wasn't marked
I did
absent.
see your email. Thank you.
Okay. Cool. Thank you so much.
Have a good one.
You too.
yeah.
Thanks.
You're welcome.
And we're still on for the test for the responders with the webcam. Is that going to
Yes.
be due for Wednesday or?
So what I'll do is your class, how late does it run tonight, Anissa?
It runs until 9 o'clock.
Okay, so what I'll do is I will make this available until 11:59 tomorrow. So if you just get it done before then, and it's actually going to be available for you because I allow you like almost 24 hours to view the corrected version. So for instance, when you go back into it, it'll not only show you which ones you did wrong, it'll show you the right answer, but it's only going to do that till like 11:59 the next day. So I will make the test available till 11:59 p.m. tomorrow, and then I will make it visible until 11:59 the next day for you specifically. Okay?
All right. Thank you.
You're welcome. Have a good one, Anissa.
You too.
Bye-bye.